Hello, everyone. I am Daniela Garcia, and welcome again to another edition of Encora Talks. Our topic for today is cloud design patterns. We have such an amazing speakers. They are Bharat Shah and Porvini Gotilla. Bharat has more than 10 years of industry experience in technology, currently a tech lead at Encora. His expertise ranges from backend systems to cloud architectures, microservices design, and agile methodologies. With a deep knowledge of Amazon Cloud Services, he specializes in microservices design, especially with Spring Boot. Purvi is a certified cloud architect and engineering manager at Encora. With more than 12 years of IT experience, she has led the development of corporate applications in a variety of verticals, such as digital commerce, fintech, and energy. In addition to overseeing product engineering, she actively participates in project delivery and process improvement as a cloud practitioner and agile methodologist. Good morning, guys. Thank you so much for being with us today. We're so happy to have you here.
Thanks, Daniela. Really excited to be here. I'll quickly share my screen here. Let me know once it's visible.
It's visible already.
Okay. Hello, everyone. Welcome to this talk on cloud architecture design pattern. This session will be useful for anyone who has basic knowledge of cloud service and is involved in application designing and implementation. As part of this session, I'll be talking about the success factors or the guideline principles for any cloud-based application. Then we'll cover around 15 design patterns based on these principles. The next section, we have included a case study where we have covered almost 7 odd design pattern out of this entire catalog. And the last section will be a question answer round. So these patterns which we are going to discuss now, they hold valid for any cloud platform, irrespective of you're using AWS, Azure, GCP, etc. To start with the success factor, the first question that comes to our mind is what is a good application, or how do we define a well-designed application? So definitely the first thing that comes to our mind is performance. The application should be highly responsive. Again, the availability of application should be maximum. Nowadays, in fact, the cloud platforms are claiming for more than 99% of availability. For data-intensive application, it should be capable of processing huge amount of data. The application should be scalable enough in case you have peak traffic hours. It should provide a seamless experience to users, scale up, scale down as per the requirement. Then on top of all these things, we also have security. So your application should be secured enough. Then, however good you define your application, failures may happen. So it should be able to handle the failures gracefully. And last but yet important, it should be a maintainable and a reusable application to make it cost efficient. So with that, I move to the why do we require design pattern? The reasons why we are talking about these patterns. The patterns are not solution itself. They inspire the solution. They help us to design the solution based on needs. These patterns are actually crafted by some experienced practitioners, and it helps us to make the application more scalable, resilient, secure, and easy to maintain. These patterns are something which are already proven and we can simply use them. So why reinvent the wheel? Again, these design patterns also act as a vocabulary for developers. So documentation, architecture, understanding becomes pretty simple with that. What are the key areas that we are going to focus on as we go through each design pattern? So we'll start with some availability related patterns. Then we'll also talk about resilience and performance patterns, followed by some data management patterns and the security related patterns. Each design pattern that we talk about will be able to, these are capable of addressing multiple problem areas. So selection of design patterns must be done appropriately based on the need of your applications. So first we start with the availability pattern. When I talk about availability, health endpoint monitoring becomes one of the most important part. Uh, there are many factors that can affect your cloud hosted application, such as a network latency and the performance and availability of compute or storage system, or even the network bandwidth between them. Your services may fail entirely or partially due to any of these reasons. Therefore, it's like advisable that we monitor uh, or these applications at various service level and at regular interval. At times, we have seen that nowadays we provide service level agreement also, where we define that we'll provide an availability of, let's say, 99% or more than that, looking at current industry standard, obviously. Uh, Alert management on top of health point on monitoring is something that adds on additional feature, like it can notify if any malfunctioning happens on the application. So alert management becomes a key when you talk about health endpoint monitoring. In cloud platform, there are various health point monitoring services available. Like if I talk about AWS, we have CloudWatch. For Azure, there is Azure Management Service. There is also Traffic Manager. There are some external tools as well available, like we have Datadog, New Relic. These are both for application as well as infrastructure monitoring purposes. Next, we move to throttling. And when we talk about throttling, it's both performance and availability related. So throttling is nothing but it's like controlling the rate at which data flow into the target. Throttling is like when your application actually faces variable load over the time, like at certain peak business hours, you may see that number of active users or the type of active users may increase, or maybe let's say there are certain application which monitors more number of user during the end of month or quarterly. There is a huge increase in number of applications. So in all those cases, you may need to have a strategy where you can handle that increase or decrease in load. One of the very common strategies could be auto scaling. Definitely, auto scaling is nothing but you are provisioning an additional resource, and this provisioning may not be instantaneous. Plus, when you are adding an additional resource, you are adding an extra cost to your application. So in that case, throttling can either act as an alternative strategy, or it may also act as an interim measure. Alternate strategy in the case where you want to keep a soft limit, that we are not going to provision more instances, let's say when it has reached to a certain limit. So that kind of soft limit can be used as an alternative. The other way could be it's used as an interim measure. By the time you provision your new resources, throttling can be done. So these are the various ways you can make use of this pattern. If I talk about certain use cases which we have usually seen in terms of throttling, like we all use address provider services, or let's say wealth monitoring services. These standard services we have seen, they provide you that this is the limit of number of times you can call an API within a minute, or this is the maximum number of times you can call an API. So that is also a good example of throttling, where you are putting a soft limit on top of it. Let's say every minute, then next minute again your number of calls refreshes. There could be multiple strategies to it, like you can do throttling at load level or at client limit level. Like I said, the other very common way could be disabling or degrading the functionalities which are not essential, or deferring certain operations based on how important it is. If I say an example for that, it could be if your application is doing a video output streaming, in that case, at certain times, you might want to lower the resolution of video until you are able to add additional or provision additional resource to your application. Next, we move to the queue-based load leveling. This is something which is widely used for asynchronous communication. In this case, the queue will act as a buffer between task and service. In this case, like you can see here, the task and services are decoupled. The task will post the message which contains the data, while service will retrieve the message from the queue and process them. So basically, the task and services are decoupled, and the application, the load over the task will not be flown to the app service level. Definitely, we'll have to have an application logic that will control the rate at which the services will handle the message to avoid overwhelming the target source. That means any spike that happens, any spike in demand that happens at the task level will not flow to the next stage in the system. And in case you need a broadcasting messages, then instead of queue, we can also use topics. Some very commonly used ones are RabbitMQ, Kafka, etc. They are available in market and are usually used for asynchronous communication. The important thing that we need to understand about this design pattern is it is useful for asynchronous communication, but in case your application is expecting a synchronous communication, like the response is expected with minimal latency, then this may not be the right design pattern for you. Next, we come to a resiliency pattern. Here we are going to talk about retry and circuit breaker pattern, which go pretty much hand in hand. So retry pattern are usually for transient fault, while circuit breaker patterns are for non-transient or the fault which we don't know how much time it may take to recover themselves. So it's like in case of transient fault, like slow network connection or timeouts, the application usually corrects themselves within a short period of time. So in such cases, implementing a retry strategy like exponential back off or retrying after an incremental interval or after a regular interval, it will help for a seamless user experience. That means if the fault is rectified by itself, the application gives a success response with a seamless experience to user. But again, it's important that we define a maximum number of retries, because if the fault that are happening due to, let's say, unexpected events which are less easily anticipated, or maybe it takes longer time to rectify, then it's pointless for an application to continuously retry. So in that case, circuit breaker pattern comes into picture, where the application should be designed to handle these failures accordingly. The circuit breaker pattern, actually, you can see here, there are 3 stages, and it is designed where if you get a success response, the circuit is called as closed. But in case of when your failures reaches to the maximum retries, the circuit is marked as open, and any subsequent request that comes in is directly responded back with the error response. So that way you are avoiding any unnecessary resource utilization. Again, there's a timeout set with the open state. So as soon as the timeout, like you have reached to the timeout state, then again the application tries to call the same connection. If you see that it still failed, it will go back to the open state. Otherwise, in case of success, it's marked as closed. So that is how you are able to handle the failures within the application. Some very good example of circuit breaker pattern could be from one of the use cases. It may be a integration with payment service, let's say. So let's say if payment service, which is an external to your application, fails due to some unexpected error and it's not able to resume back, we don't know how much time it would take to recover. In that case, it doesn't make sense that we make that try again and again, keeping your user waited, right? So we can mark that circuit as closed, open, and then as soon as the user tries to make a payment, they can be shown an error and it can be gracefully handled. The next one, we move towards a static content hosting pattern. It's very widely used for performance and scalability purpose. So with static content hosting, I mean the content like static pages, images, videos, any kind of digital asset that basically doesn't require a computing. Uh, these static content can be hosted on cloud-based storage services like S3 bucket or blob storage, etc. And because these content doesn't require any kind of computation, obviously it doesn't make sense to put them on a computation engine because these computation engines are costly. So again, hosting them as a static content comes with a cost benefit. Again, these static content, when they are hosted on uh, let's say any CDN, they can stay near to the user's geographical area. That means again we are reducing the latency, which comes with a performance benefit. Some very commonly used CDNs could be CloudFront, Cloudflare, StackPath, etc., which can also be used for content hosting purposes. With that, I'll hand it over to my friend Bharat, who will continue with the data management patterns. Bharat, over to you.
Thank you so much, Purvi. So Purvi has covered many design patterns which talks more about performance, scalability, and availability, right? Now there are a few more design patterns where you should also take consideration of your data management and security. Okay. So one of this design pattern is caching. So when we talk about caching, right, in which scenarios we should consider that here there is a need of caching. So we need to understand first that caching is useful in a situation where there is a no requirement of getting the data again and again from the data servers, right? You can cache the data in your local server. You can cache the data on the instance that is very close to your applications. And that's where you can get the data. Now, in order to do that, right, we have a couple of options. As you can see, there is a lazy loading option available there. There is a proactive option also there. In lazy loading, right, what we generally do when client make a request for particular data, right, it checks first in the cache. If that is available, data will be returned. If the data is not there in the cache, right, it make request to the data actual database. It fills the cache and return it to client. So that's where this lazy loading works. The second way to do the same operations, right? Ultimate goal here is to just get the data near to our location, application location where the data can be retrieved fast. So the second way is a proactive caching where application updating the data in the database. As soon as the data is updated in the database, right, you are just updating your cache as well. And that's where the data in the cache is always active. That is a proactive. So this is cache design button, and we should consider if such need arise in our application. Yeah, or you can next move to the next slide. Okay, one of the famous, I would say, design pattern here is command and query responsibility segregation. So when we say what is command and what is query, okay, so basically this design pattern divides your entire application into two parts, command and query. Okay, but before explaining what is command and query responsibility segregation, I would like to explain that when we should use this pattern. So in certain situation, it may happen that when we compare our read operation with our write operations, right? The scalability are not equal. We want more scalability in the read operations, right? In certain type of situation, what we can do, we can divide the responsibility. You can use a service who continuously write the traffic, write the data into the right database, okay? And there will be a separate set of read services who can get the data from the events, right? So when I say events, here one important point to consider is that your write service, when it writes to the database, right? It puts the events, stream of events in the event train, we can say that is a source of truth, right? It put the data into that, and that's where your read queries or read consumer or read service consume the data from that, and that's where they make the data up to date. So you are dividing complete responsibility. Yeah, right. But important point here is that we should only use this pattern where there is a real requirement of different need of read versus write. And you don't need too much of write, then you can just divide this in the write services. And if you have a lot of services which are read centric, data availability of data is more important, right? That's where you can just select read services. That way you can divide the responsibility. And materialize view, that is nothing but on top of your read services, right? It creates the view. It can be a different database, okay? It can be a completely different structure. Your write can be a NoSQL where you can immediately write in the database, but your materialized view can be something else, right? It can be a different database like MongoDB, right? And using that, you are generating a view just as a purpose of providing the data faster. So that's where this command and query responsibility segregation design button comes into picture. Purvi, we can move to the next slide. Okay. So this design pattern is similar about CQRS pattern. We will call it event source pattern. So when we use CQRS pattern, right, we will have to use event sourcing pattern. You remember I mentioned that when we get data from the client, let's say you are placing an order, right? And you are not updating your database immediately. You are just putting your data as a sequence of event in the event store. Just imagine if you don't use this pattern. So generally what you will do, you place customer place order, it will be stored as a relational or non-relational way in the database. But here we are not doing that. Instead of relational way, instead of row in the database table, we are just putting the events in the event store. So that's where it comes. It called event source, right? We are just putting the event source, and as soon as we are putting the event source right in the event store, we can write n numbers of listeners out there who can just read the events, replay the events, and fill up the read replicas. I talked about read replicas, right? They can fill the data the way they want, right? That can be completely different materialized view, that can be completely different data structure. But the idea here is that here we have completely divided responsibility of read and write using the event sourcing pattern. Okay, that's where we need to understand that where we can use this pattern, right? Where there is a no requirement of as soon as synchronization of write data to read data, because there will be some lag, right? When you write something to the right events store, and there will be a bifurcation, and when your read queries will pass to the read replicas, that will be some time difference. So you will need to carefully consider the situation where you can use this event source pattern. Okay, uh, Purun, you can move to this next slide. Yeah. So one of the good design pattern among all of this, which I like most, is the sardine design pattern. Here, generally, when I say sardine design pattern, right, what it means, it divides your data, right? Let's say you have one application where there is a large chunk of data being stored, right? And day by day, the data is getting increased and increased. So rather than having them in a single instant, rather than having a read replicas for single instance, which stores only single data, right? What you can do, you can actually divide the data, right? And that's where it comes sardine. So here, how you can divide the data, that is a role of sardine strategies, right? If I provide you an example, you can simply write a starting strategy in a such a way that all the data which starting from A to I can be stored in the different data. All the data whose last name start from J to R can be stored in the different database, and all the data whose last name start from S to Z can be stored in the different database. So there comes sorting of the database. Whenever you implement this pattern, you will have to make sure that the sorting instances which you have created or which you are going to create, right? Those are close enough, and your aggregator, right? When it collect data from different sardines, different sards, right? The performance is super fast. So this all consideration we will have to take care. The important point is that this is a required pattern when you have so much data, and it is getting increased day by day. That's why you can't have a single data instance or single table which holds all the data, because your query will take so much time to execute, right? And that's where you will have to, at one point, you will have to decide to break the data in the shards. And that's where it comes with the sorting pattern. Many database are performing very good with the sorting practices. The example is MongoDB have very good sortings. We all know that. So that's where we'll have to consider this pattern when it really needs it. Okay. Yeah, Purvi, you can move to the next slide. Yeah, one of the design pattern is patriarchal identity. So here, this simply says that we should have a single source of identity. Just imagine you have five microservices, right? Rather than implementing authentication check in each of the microservice, right? You should have a single identity, single source of identity, where any service or any client wanted to check the identity of user, right? It can interact with that, it can generate a token. Okay, that token can be used to access their microservices as well. Now the single source of microservice which I'm talking, right, which I named is identity service, can be connected to many providers, identity providers. It can be a Google, it can be a Apple, it can be a Facebook, it can be Instagram. So the advantage of identity, you don't need to write the identity logic everywhere. You should have a single source of identity where you can just pass your username and password. Identity service take care of it. It will interact with any third party microservices required and generate a token for you. It will have proper claims inside it, which provides authority, right? Which data you can access. So that's where come identity, patented identity evidence. So we need to make sure that we are not writing a microservice in such a way that each microservice have different logic for authenticating the user. Okay. Yeah, Purvi, you can move to the next slide. Yeah, so the one design pattern here is gatekeeper design pattern. Okay, as the name suggests, it is a gatekeeper, someone standing at a gate, just securing the resource. Okay, so just imagine, see the diagram left hand side where client is making a request to the trusted host. That can be our microservices, that can be our database services, right? The thing is that before even reaching to the trusted host, right, we have intermediate gatekeeper. This gatekeeper's responsibility is just to sanitize the request. It will validate the request. It will validate that proper request is made or not. This separate agent, or I would say the separate host, which we are putting separately, right, as a gatekeeper, it will provide us a flexibility to avoid all kind of security attacks like SQL injection, cross-site scripting, DOS attacks, right? This gatekeeper has very less information about your resources, and that's the catch. Even if that get hacked, right, the attacker will not be able to access any resource information, right? Because this gatekeeper has very limited information, and that's where it just validate or sanitize your request, and if that is valid, it will pass it through a trusted host. And just you will have to consider that gatekeeper should be separate instance. It should not be a same instance as your application server. Okay, this is one thing we need to ensure that. Okay, Purvi, you can go to the next slide. Valid key pattern, yes. So here, the primary focus of this valid key pattern is that it provides cost, performance, and security benefits. So we all have a need where we don't want it so much of network traffic in the entire application. Let's say if I take example of uploading something on S3 bucket, let's say. Okay, so here rather than clients interact with the backend APIs and backend API takes the responsibility of uploading something, right? What we can do, we can generate certain kind of tokens, okay, and provide it to the clients. That token provides limited access to bulk of a data where user can directly upload something. So that's where what you are doing, basically you are delegating the responsibility, but during the delegation also you are making sure that proper authentication and authorization check is there or not. So here the sequence would be like this: agent or client make a request to your backend server, backend API that, hey, I need to upload something at this location. Backend API will ensure that this user is a right. Okay, and that's where it provide a pre-signed URL or some token which is valid for certain period of time. And using that particular token or that particular signed URL, they are uploading material directly to the S3. So this is called valid key pattern. And that is useful. We should not provide a direct access to our client as well to upload something, because it will be a security loophole. So this pattern we need to make sure in certain type of scenario which I have mentioned. Okay. Yeah, Purvi, you can move to the next one. Okay, so all of this design pattern, right? Performance, scalability, availability, which Purvi has discussed, and the latest section which I have discussed about data management and security. We have few case studies uh, which have flavors of most of this microservice, most of this is design patterns, right? Which we have. Purvi is good. I would like Purvi to explain this case study. Purvi, hand over to you. You are on mute, Purvi.
Sorry. Yeah. Okay, thank you, Bharat. So I think we have gone through a wide catalog of around 15 design pattern, and I've tried to put down that into a single study where we can relate this with a real-time system. Uh, so we actually had so this is something which is inspired by one of our client projects, where we had a requirement that for an existing e-commerce platform, they wanted to extend the capability to support multiple product line and customer workflow, while also keeping into mind the performance of the application. Like we know, in e-commerce, performance is one of the key factors. So here is something I have where, it's a good example where we have implemented these 8 odd design patterns. Uh, like you can see in this diagram, it's a backend e-commerce system, and the client actually wanted to retain that e-commerce system. There's no change that was supposed to be done in their legacy system. So this is more like an example to hybrid uh, a hybrid kind of architecture, where you have a portion of your application sitting uh, in client's physical location maybe, but in this case it was another cloud system, so I can call it a multi-cloud system. Like you can see, there is a small dashed box in this diagram, so that is particularly to define the area where we worked on, and it was all deployed on AWS services. AWS cloud services were used. The first thing that you see in this diagram is that API request comes in and hits API gateway. So very much in connection with the pattern which Bharat talked about, the API gateway pattern, where it sanitizes all the incoming requests. So this is where the API gateway validates, it checks whether it's coming from the authorized person or not, and then accordingly it is redirected to the right service. Now, in this case, we used microservices pattern. So API gateway also helped in redirecting it to the right Lambda service. While in case if the app is the if the request is to be directed it directly has to go to backend system, especially in case where the order placement was done, any write request is to be done, it is directly moved to their existing e-commerce system. So you can see that big arrow which says any write command. So that is where API gateway came into picture. There was a centralized identity management system already existing. And again, it's not a good idea to add multiple identity management. I think Bharat already mentioned, it's more like, centralizing the entire system. And then you are offloading the entire load of, generating the tokens, etc. So that is the same thing we did. We utilized their existing identity management system. It continued creating signature, and we just used a validator API from the existing system to sanitize the request. Apart from that, you can see there is a S3 bucket. There is an Elasticsearch. So that is where synchronization of data was required. The first thing which I can explain here is that how the files were put into S3 bucket. So there is an existing e-commerce system, while there is certain data which only is required for pre-checkout journey, let's say. Pre-checkout journey, I mean, you see PDP or like a product description page or product listing page, or those pages which are actually that drives the maximum performance uh, capability of your application. So any user which comes to the application, they first want to look at your products, right? That is where you have to work a lot on performance side. So for that purpose, we had placed a S3 bucket where the backend system was dropping the files regularly, and this was done using a pre-signed URL. So there is a call out of valet key pattern. That is what we used here, a pre-signed URL with a limited time and accessibility. Again, like you can see here, the entire write communication is happening with the existing e-commerce system. So write communication, I mean anything which is related to post-checkout journey. Once I've selected my items and I put it into cart, now the order placement can go into the actual e-commerce system. While you can see the entire read part is going through the microservices. That means I've enhanced the read feature of the application. So that is where you can call out a CQRS pattern. I have uh, decouple the write command from the read command. Again, that means your performance is improved. Also, when you show your product in a listing page, you have multiple products. You don't want to show all the details on the listing page. While when you come to detail page, you want to show each and every detail, like what's the quality, what's the material, when it will be shipped, etc. So in that case, we have used Elasticsearch, which acted more like a materialized view. That means we just took a portion of data from the Aurora database. Aurora database is a relational database we used in this case. We took a portion of that data and it was indexed in Elasticsearch, which even enhanced the performance of application. On top of all this, we used health monitoring by using CloudWatch, and there could be many other external applications that can be used for health monitoring purposes, like I mentioned some New Relic or Datadog that can be used at both infrastructure and application level. So this is how we have designed the entire architecture to support customers' requirement. So with that, we come to the end of this case study. The next will be a question answer round. So
Thank you
yeah,
so much, Purvi and Bharat, for all this valuable information and knowledge you have shared with us. As you just mentioned, we're ready now to start with our Q&A section. So the first question I have for you guys is, for microservice architecture with respective DB, how do we handle transaction management and rollback?
This is a very good question. So here, basically, when we decide a microservices, right, we obviously opt for a different database. And when there is a different database, it is critical to decide how we will maintain rollbacks, how we will maintain a transactions, right? So here, in order to achieve this transactions, this rollback, along with all the design pattern which we have a separate pattern for that, which is called a saga pattern, where what you can do is you will have a sequence of local transactions, right? If you talk about order, right? You place the order, that is the first transaction. Once the first transaction is completed, you can move it to the next. Based on that order, there will be a certain type of check as well, right? If you wanted to check customer's credit limit, right? So there will be a second transaction, but that will be a local. So there will be a set of local transaction, which is called saga pattern. And if one of that fails, we'll roll back. We roll back, right? And that's where we roll back entire transaction. So in this microservice, right, where each microservice has separate database, and if wanted to achieve the transaction, there is a dedicated, studied, and already investigated design pattern, which is called a saga pattern. I would like to suggest that to use.
Thank you a lot, Bharat.
Yeah.
The next question is, in case of data coming out from multiple microservices, how can aggregation be done?
Oh, okay. Yeah. So here previously it was about transactions, right? But the core was the same, that data is segregated. And here also, when each microservice dealt with a separate database, and now in certain situations, we required that we wanted to collect data from all of the database, right? We should never implement something where single microservice directly interacting with each database, even though there is a separate microservice for that. Big no for that. Here to deal with this situation, right? Since all of the microservice has separate
Mhm.
responsibility to just interact with that database, what we can do, we can just write API gateway, right? There is also API gateway microservice, which that is API composition microservice or API composition design pattern, right? What it does, it get the data from all the microservice which is required and serve the data to client. That's where we can just utilize the data from all the microservices and serve it to the requester where it required. This is one of the way, right? In certain situation, as Puri mentioned, there is a materialized view as well, right? Where we can just generate a service which is for a faster performance because it may require, right? In certain situation, we wanted to treat data, we wanted to access data in certain way that is very faster. So in this situation, we can create a materialized view that is indexed properly. That is, Purvi mentioned that we can use elastic search as well, right? So all of this we can do using materialized view and serve the data. That's where we should do data aggregation.
Thank you
Yeah.
again, Bharat. Guys, the last question. Do these patterns hold valid for hybrid architecture as well?
Um, so let me take that one.
Sure.
I think in the case study itself, we saw a good example where there was an existing e-commerce platform which client had, and they were not willing to move that or change that. So in those cases, it can either be a hybrid pattern or, like I said, in our case, it was multi-cloud. But in either cases, these design pattern equally holds good. Uh, one of the examples is identity provider I mentioned in the case study as well. So that is where you can still make use of the existing systems of client, while on top of it your cloud uh, architecture sits, which is majorly for enhancing. And in fact, we have done that widely for many clients where we have uh, made use of their existing system until they completely plan to move from their physical servers to cloud. So there is a transition period, right? And during the transition period, we usually see these hybrid model. While there are certain constraints also where the clients, especially in case of health sector or banks, which are still not ready to move their data to cloud due to certain constraints, certain compliance rule. Though we have data sovereignty in place right now, but yeah, people are still hesitant to do it. In those cases, yes, we go with the hybrid model, and these patterns hold equally good with these design pattern, because you can extract only the required amount of data, create a materialized view on top of it, or maybe have a read database on top of it, which can cater your requirement. Definitely, it will improve the performance of application.
Understood. Thank you so much for being. Thank you again, Bharat, for everything, for being with us today. And thank you everyone for joining us. Please keep an eye out for more webinars that we will be hosting soon. We also invite you to watch the recorded webinars we have posted on talks.incora.com. Thank you so much. I hope to see you soon.